Okay, so we will be recording this part of the session, so if anybody has any objections, please say so now. Okay, so up to this point, we've been talking about the types of control actions, and so we had talked about the proportional action, which is basically a variable gain that we're providing the system. So the control action is going to be directly proportional to the error. The larger the error, the larger the control action, vice versa. Um, then we talked about the integral control. And so basically what the integral control does is that the integral control is going to basically modify the transfer function because it's going to add a pole in the denominator. And that pole in the denominator is going to automatically increase the type of system that we have. And so by increasing the type of the system, it's going to automatically affect and improve the steady state error. Okay, the steady state error. And so that is an integral action. So the combination of the proportional and the integral, it's called a PI controller. So the proportional integral controller is used mainly when we are trying to improve the steady state. And then we talked about the derivative controller. And so with the derivative controller, what is the, oh, and let me backtrack a little bit. In the integral controller, why is it affecting the steady state? Because it has memory. It is accumulating the error. It's accumulating the error somehow. And it's taking an action that is proportional to the accumulated error. And that's why it says that it has memory. The proportional action is looking at the present, it's only amplifying the error. The integral action is looking at the past, the accumulated error, and it's making an action based on that. And then we've got the derivative action. So the derivative action occurs when we are looking at the rate of change of the error, meaning how rapidly the error is increasing or decreasing. And so for the transient response, where we've got an overshoot, we're going to have a rate of change of the error, which is going to be basically the how fast the error is increasing or decreasing. And so the control action is going to be proportional to that. And so how is that going to help? Well, if the error is increasing, the proportional action is going to, the derivative action is going to act. And so it's going to help us with regards to the transient, or and what parts of the transient are we looking at? We're looking at the overshoot. We're also looking at the setting time. So that's the proportional derivative action. The proportional derivative action is said to be trying to see the future because it's looking at the rate of change. And so when we combine the proportional, the integral, and the derivative control actions, we get what is called a PID controller. Okay, and so the PID controller in its most general mathematical representation is going to be this one, where we're going to have the error, which is identified here as E of t. The error is going to be affected by a proportional action. It's going to be affected by the integral action. And lastly, it's also going to be affected by the derivative action. So the combination of the three, it's called PID, or proportional integral derivative control. And so each of the separate control actions have constants associated with it. Usually it's an integral time and a derivative time that are used. And Kp is multiplied by these. And so we have a combination of different constants here. If we look at it as a transfer function, then each of these gives us each of these components. So this one here is going to be the proportional action. This one here is going to be the derivative action combined with this one. I'm sorry. This one here, I'm sorry, is going to be the integral action. Which one is that? No, I'm sorry, I'm making a mess here. This one is going to be the integral action, and this one is going to be the derivative action. The other thing that's important is that the integral is going to add a pole at 0 in the denominator that increases the type of system. The derivative is going to add a 0 that's going to reconfigure or move our root locus towards a performance value that we're looking for. And so another representation of the proportional integral derivative controller. Just noticed a mistake here. Proportional integral derivative controller that we've got here is this representation where we kind of integrate the constants. So we've got Kp, Kd, and Ki. And actually, really what we're going to end up having is we're going to have three constants, which is the proportional, integral, and derivative constants. And those are the ones we're going to be playing around with. And actually, in commercial PID controllers, you're going to get the controllers and you're going to be able to modify each of these three constants that hence is going to modify the behavior of the system through the controller. And so this combined action serves to both improve steady state and transient responses. And we can convert a PID controller into any of the other combinations by eliminating either of the constants. So if we eliminate the derivative, we get a PI controller. If we eliminate the integral, we get a proportional derivative controller. And so the combination of these three is usually what we see and usually what we get commercially. Okay, how do we design based upon PID controllers, or how do we design a PID controller, which is kind of like the end game or the closing the loop of this course that kind of integrates everything we've seen up to this point. First, what we do is evaluate the system without compensation. So assuming that we don't have a controller and we evaluate how the system behaves, we're gonna see a certain behavior with regards to, again, transient and steady state responses. So we look at that and then we say, okay, I want this or this improvement. Once we look at the uncompensated version of the system, then we incorporate the proportional derivative. So we try to play around with the proportional derivative until we get the transient response we have. Then we simulate the system to see if the PV controller, is doing its job. If it doesn't, then we go back to step 2 and keep tuning. Once the transient response has been established, then we just add a proportional integral controller to help satisfy the steady state response. Once we do that, we're going to have the three controller values. We simulate the system to see how it behaves. If somehow we need to tweak something, we go back to steps 2 to 4. Okay, so this is why it's called PID tuning. It's kind of like tuning a guitar. We want to get to a certain note, so we kind of listen. If it's too low, we strengthen the string. If it's too high, we lower the tension until we get what we want. And so that's why it's called PID tuning. And so this is kind of a summary of each of the controllers. So again, the PI is going to improve steady state error. It increases the system type. We can add, so the pure PI controller is just to add the S, but really we're going to add an S plus something. So that's something that we're adding, can be very, very small. So it's very close to the origin, and that means it's very close to 0. Then we've got the proportional derivative. The proportional derivative is going to improve the transient response. We have to be very careful with the derivative action, because if we don't regulate that one correctly, then we're going to have saturation, meaning there's going to be too much amplification. There's going to be too much of an action and reaction in the system that's not going to be practical. That's why that's the first one we try to tune. And in the end, we get the whole combined response of the for improvement of steady state with the PID. And I've incorporated some videos that kind of give the same explanation I just gave here. So we also have those.